Thank you for joining. My title today in this paper is Opportunities for Offshore Wind Energy and Large-Scale Sequestration of CO2 in Basalt Rocks, the Kerguelen Island case. Purpose of the talk is to present a solution for upscaling carbon dioxide removal from the atmosphere as part of a set of actions that would be necessary to address global climate change. But looking in particular at an extreme setting, the Kerguelen Islands in the southern Indian Ocean, which will provide some perspective on the technical requirements and the implications of this kind of solution for climate mitigation, particularly the drawdown of CO2 from the atmosphere. The outline for the talk will be first to present some negative emission technology motivations and the background information about carbon mineralization, which is also a negative emission technology, and a mechanism to store CO2 safely for long periods of time in solid form. Looking also then at the technologies available to us today for direct air capture of CO2 and the potential for offshore storage of CO2. This leads us to look at the very large potential at the Kerguelen Islands themselves, and in particular the wind energy resource that is available there, and combining that with capture and storage needs to make this if you will, a wind carbon capture hub. And then some concluding remarks about where this research has led and what the implications and trade-offs would be for designing this kind of solution for mitigation of climate on a global scale. So motivations for negative emission technologies and the targets that have been set by the IPCC, the Intergovernmental Panel on Climate Change, will require hundreds of billions of tons of CO2 to be removed from the atmosphere, not emitted to the atmosphere in order to meet net zero targets by mid-century. This assumes that major technological and behavioral changes will happen in our use of energy and our emission rates, as well as the development of negative emission technologies, tools that allow us to remove CO2 from the atmosphere. Those are required in any scenario because of the need to reduce hard to avoid emissions, such as those from long haul air travel or certain manufacturing processes, such as cement and steel production, and also to accommodate any delay in achieving those efficiencies and reductions in emissions, which is sometimes referred to as overshoot, and that to do that, the emissions would be in the atmosphere and would require to be removed, thus the negative emission name. And that is indeed something that might reach 5 to 10 billion tons of removal required by net technology over the century. So with that motivation, the opportunities using carbon mineralization are one of several both engineered and natural net type solutions, which also include biological and other approaches to remove CO2 from the atmosphere. Carbon mineralization approaches are illustrated here and include natural ones, such as natural weathering of rocks that are in contact with the atmosphere, drawing CO2 into them by mineral reaction at the surface. And there are engineered solutions, such as the mineralization of mine tailings, which react in a very similar way, capturing CO2 and storing it in permanent mineral form, typically in carbonate. Also combining on the right-hand side of this figure, engineered systems such as direct air capture, which we'll talk more about, as well as chemical looping or perhaps even point source capture of CO2 with storage, injection and storage of that CO2 in subsurface formations of basalt and peridotite, where similar mineral reactive processes occur, capturing that CO2 and converting it from carbon in a low oxidized state to a carbonate. So the approach here is primarily a engineered one, and we're looking particularly at the direct air capture technologies, which are systems that basically enable CO2 to be scrubbed from the air. And the capture process itself takes high concentration CO2, relatively high concentration, say 400, 420 ppm CO2 in the atmosphere and ambient air, which is then driven across a contactor surface, and CO2 free or CO2 depleted air is returned to the atmosphere. A stream of fairly pure CO2 is then available for use for other purposes or for storage. And in all of these systems, a significant amount of energy is required, both to capture the CO2 by driving the air across these contactors, as well as for the process of absorption and adsorption, which require energy to remove the CO2 from its bound state on those surfaces, on those filters, for example, and return them in a capture cycle to allow more CO2 to be recovered. All three of these systems require energy, and we're going to look at primarily the energy needs for direct air capture itself, and the storage opportunity that we have available to us in this remote location. The transportation issue and compression issues and costs in terms of energy are important. We're not going to focus on that in this study, primarily because these systems are identified to be co-located in a nearby location. But of course, this is in most environments, most other environments, necessarily transportation and compression are critical pieces of the energy balance. Another opportunity that is possible when looking for renewable power to be used for direct air capture and storage, which is the left-hand side, if you will, the left-hand part of this image, which is our investigation today. An alternative is to use renewable power and captured CO2 and a portion of that power to create products, in particular fuels. And this is an approach that is being used in some of the commercial applications today, where direct air capture is being converted to usable low carbon fuels and from renewable energy. This is certainly viable and not a primary focus here. We are looking at renewable energy, direct air capture and storage, so that to investigate what would be required if CO2 were to be used uniquely for climate benefit. So there are a handful of commercial ventures being undertaken today at the pilot, laboratory pilot, and even plant stage for demonstrations of prototype direct air capture efforts. The two companies that I want to point out from this list, which arises from the National Academy study a few years ago, that are active, very active in the field. One is Carbon Engineering in Canada, using one methodology that we'll discuss in a moment, and have pilot plants that are scaling up to as much as 1 million tons of captured CO2 per year. And the second being Climeworks, is a Swiss company, which has active demonstration plants, a number of them around the globe, at hundreds of tons per year and scaling up to thousands of tons per year. And there are a number of commercial ventures that have been undertaken in other countries and using similar related as well as new technologies, developing new approaches to directly capture CO2 from the air. And these are all viable, but we're concentrating in the existing plant and prototype and demonstration phase products with two of the techniques that will be discussed here on the following slides. The first one was discussed as described as a liquid solvent system. This is analogous to the carbon engineering approach. And in this case, the direct air capture is accomplished by forcing air across a reactor with liquid alkaline solutions, such as a calcium hydroxide, which is absorbed on in a reactor and precipitates calcium carbonate. That calcium carbonate then requires a significant amount of energy in a calciner, a high temperature kiln, essentially, to remove the carbon dioxide from the carbonate, producing a carbon dioxide stream, and returning the calcium hydroxide to the solution as in a recycling process for a next regeneration process for another cycle of capture. So the left-hand side of this image illustrates the capture side of the system, and the right-hand side of the image illustrates the regeneration side of the process. It is important to note that with liquid absorbing systems, that the calciner temperatures are typically quite high, 900 degrees Celsius, and require significant energy, of course, to reach those temperatures, usually using natural gas or electrical power. Such systems have been in development for, or in use in commercial processes for many, many years, and have recently been studied as prototypes, first of a kind, for direct air capture, with estimates on the order of 9.9 gigajoules per ton of CO2 produced in a combined sense, and a commercial goal that's published for reaching roughly half of that energy requirement of about 5.4 gigajoules per ton of CO2 produced. In solid sorbent systems, these are systems that absorb CO2 from ambient air on a solid framework, usually with amines or amino groups that are on that solid framework, also require air to be driven across that filter, and also require a significant amount of energy to be used to regenerate the CO2, regenerate the filter for recapture of the CO2 cycle and production of a CO2 concentrated stream. These systems are not unlike the systems that have been used for many decades in air purification systems, for example, in aircraft or in submarine, and function not unlike a catalytic converter in an automobile. The process of driving the CO2 off of the filter can be done in a variety of different ways, through changes in temperature, pressure, changes in humidity, or combination of the above. And the activity here is, again, in new developments are active. Recent work has shown first-of-a-kind examples in the field to require about 9.7 gigajoules per ton of CO2 produced, and with a commercial goal of approximating half of that, about to 5.5, maybe slightly less, in turn 5.5 gigajoules per ton of CO2 produced. And as mentioned, there's a number of active commercial ventures looking to improve both materials as well as the efficiency of the energy regeneration process. One of those combined approaches is illustrated here. This utilizes simply a heat pump and a vast resource of cold water, in this case seawater, to regenerate a solid adsorptive system, driving CO2 off a collector, and using the temperature heat pump system to freeze CO2 out as dry ice, and be quite efficient in terms of the energy requirement. This may cut again the requirements by a factor of 2 to as low as 2.3 gigajoules per ton of CO2, and other combined systems looking at electrochemical combinations, electrification of the system may drive the energy requirements even lower. These have been developed and continue very actively to generate a system that may be in the future a much more effective, or at least twice as effective as what we're assuming in this study. We are using the commercial goal as our target estimator for amount of energy used, about 5.5 gigajoules per ton of CO2 produced with the current prototype DAC systems. So this is entirely a theoretical model. The example I want to point out is a project in Iceland where CO2 is being captured from a geothermal power plant using energy, waste energy, and from energy from renewables locally to inject that CO2 into basalt rock on land in the area. This is the CarbFix project, and the CarbFix project illustrates the ability to both inject and convert that injected CO2 into carbonate minerals in the basaltic rock that are below the plant, essentially in Iceland. The direct air capture unit has been from Climework system. This is the solid sorbent framework system, has been added into the project and piggybacks essentially capturing CO2 from the air and co-injects that with the CO2 from the power plant and local groundwater. The concept that this is an active project and as a prototype can be moved to the nearshore and to the offshore environment will require that both the source of CO2 needs to be expanded significantly, such as the direct air capture systems will need to be greatly expanded, as well as a source of energy beyond the geothermal power plant to drive the system, drive both the capture and the injection. The advantages, of course, is that the basalt resource is wide and far-reaching in the offshore environment, as is the availability of ocean seawater and the availability of a renewable energy resource, in particular wind. So we look more closely at the wind resources around the globe and where they are coincident with potentially large storage resources in basalt. And that led us to the Kerguelen Island archipelago, identified just the Kerguelen Island itself as a small black dot in the lower diagram. But illustrated as well is the global mean wind speed map in the area that both basically 24/7, 365 days a year, wind resource in the southern oceans is quite large, at reaching as fast as 14 meters per second and quite consistent in direction. In the northern hemisphere, it reaches similar velocities, but it is more variable over seasonal times. And this then led us to look at the Kerguelen Island in more detail. And you can see in this image that the mean wind speeds in Kerguelen are very stable and consistent, driving nearly 10 meters per second all through the year. And in comparison, the wind speeds in the North Atlantic, Shetland Island, or Orkney Island, for example, are quite strong, and these are potential locations for future offshore power, wind power installations. But even the variability of at these locations and the differences in mean wind speed of about 30% less than a Kerguelen account for something like a factor of 3 less net potential power available from the wind flows at Kerguelen. They're also some of the most usable and dense sea level air in the world that exist without heavy snow or temperature extremes. Although the temperatures are relatively stable, they are cold, and the relative humidity is also stable but humid. So using the advantage of Kerguelen, we look more closely at the potential of actually building installations in the onshore and nearshore environment on the Kerguelen Island itself. That is illustrated by the contour of with 50-meter water depths and 100-meter water depths. On the right-hand side, on the eastern portion of the Kerguelen Island and the flat Courbet Peninsula. And these contours were chosen corresponding to basically the tripod and anchored existing offshore turbine systems to date, capable of about 50 meters water depth to about 50 meters water depth, and floating and tethered that are starting to be installed fairly widely around the globe, capable of reaching water depths of up to 100 meters. So using these two approximations as reasonable areas, we calculate net area of about 1,400 kilometers square at the 50-meter depth and about 4,000 kilometers square at the 100-meter depth for potential installation of a large wind farm. These are large wind farms. In fact, even the 50-meter depth wind farm is about the size of the largest planned wind farm in the North Sea, and considerably offering greater wind power because of the steady and high wind speeds. So using those calculations, we were able to assume, and some assumptions about what our capability for producing wind power with current technology. We assume 15 megawatt capacity for turbines per square kilometer, with a roughly 1 to 1.5 kilometers turbines per square kilometer installation. That turbine size could be optimized with more detailed analysis of the location and what is easily deployable in this location. But the consistent wind speed in particular and the steady strong wind speed let us assume a fairly high power availability, a turbine with low intermittency of about 67%. This is a bit higher than offshore wind farms to date, about a third higher, but the assumptions based on the wind speed and direction make this a reasonable, if optimistic, parameter to apply here. So given our calculated areas for 50-meter, 1,400 kilometer square water depth, we calculate 125 terawatt hours of potential energy, or 21 gigawatt hour faceplate capacity. And for the 100-meter water depth, 4,050 kilometers square area on and offshore Kerguelen, 356 terawatt hours, or about 61 gigawatt faceplate power potential from wind. These are very significant, large volumes, large potential power amounts. The 356 terawatt hours is about the entire usage of UK power in 2019, and about half of the total global wind production in the same year. So these are extremely large potential resources, renewable energy resources. And using our capture method at our commercial goal rates of efficiency, about 5.5 gigajoules per ton captured, using that amount of electrical energy would capture 82 megatons of carbon dioxide on an annual basis from the 50-meter water depth area, and about 233 megatons of carbon dioxide from the 100-meter water depth area. Note that this is an important takeaway, that about a quarter of a gigaton is captured with this installation, so that 4 of the installations of this size and this quality would be required to capture a gigaton. And a gigaton is about a fifth, or maybe even a tenth, of what is estimated as to be required to meet some of the negative emission goals outlined at the beginning. So with that takeaway, we also looked a bit further at what would be required in terms of land area for an installation of a capture farm to achieve a quarter of a gigaton of capture per year with the wind resource at Kerguelen. And we use assumptions made in the development of planning for the carbon engineering system, which designs essentially a contactor wall with 20 meters height, and we assume that there is 10 times that distance in an array of walls per kilometer, that the contractor area in the wall is 2/3 of that full area, and that the efficiency of contact for capture of CO2 is about 75%. That leads us to the published values for capture efficiency per meter square of contactor surface with the system of 22 tons per meter square per year. And that's about a tenth of the volume flux of CO2 through a system like this in Kerguelen, where wind speeds can be are assumed to be about 10 meters a second on average. So with that assumption, we calculate 158 square kilometer capture farm area would be needed, and it is notable that it could be placed on land and adjacent to the wind farm on the Courbet Peninsula, and that this is an area with as shown by the box, about a 13 by 13 kilometer box if it were designed in that location. The last piece of the puzzle is just to briefly cover the storage requirements for a quarter of a gigaton of CO2 if it were captured by an installation of this sort at Kerguelen. Kerguelen Island Plateau is identified at the end of the arrow as that large purple shape. That is about a 6 million square kilometer area. Kerguelen Island is just a small 6,000 square kilometer area in the middle of it. That has evolved over 100 million years of sequential depositions of basalt lavas. And the storage capacity estimated from previous studies of scientific drilling are that 1,500 gigatons of CO2 could potentially be stored in this location with fairly conservative reservoir capacity assumptions. And even further, further conservative assumption that if only 1% of that capacity were available, the quarter gigaton CO2 captured with the direct air capture Kerguelen wind hub could be stored for over 60 years. The storage could occur for 60 years or more. And storage would occur very much in a manner similar to what is being conducted in the pilot in Iceland, where injection into porous basalt aquifers would convert in time to with water from CO2 into carbonates, being solidly and permanently stored. So to conclude, this study has looked at the notion of combining massive wind energy resources to current technology and prototype stage for technologies for direct air capture and basalt storage with mineral carbonation as a negative emission technology in a very remote place in the Courbet Peninsula, in particular in the shallow surrounding seas in the Kerguelen Islands. We calculate with our evaluation, energy and capture infrastructure could be used to cover a very large area, 4,000 square kilometers, to net a quarter of a gigaton of captured CO2 per year, and with virtually unlimited potential for storage of that CO2 in the nearby underlying basalt formations. Interestingly, there is essentially no competing agriculture or energy needs for that potential wind energy around near Kerguelen, which allows us to make full use of a wind carbon hub for climate benefit. And it gives us some perspective on what it would take to install systems of this nature. Four systems or more would be needed of this size and quality would be needed to capture a gigaton per year. It also brings into perspective the trade-offs to find areas that this might be feasible, such as Kerguelen, which are either very remote, incurring both cost and installation, high cost and installation trade-offs, and the fact that it is a relatively pristine and reserved area in Kerguelen, a natural resource, or at least was a natural resource that was exploited in the past, and will be the kind of decision for these resources that will need to be addressed in the future. The benefit of capturing CO2 in a place where the resource is so massive might have been considered more in the past when Kerguelen, which you see an image of here in the background showing the flat-lying basalt layers, across the natural harbor and on the Corbeil, the flatline Corbeil Peninsula in the foreground, along with the remains of the energy industry from about 200 years ago, when Kerguelen was a hub for seal and whale oil production, exporting something on the order of 150,000 barrels of oil to Northern Europe on an annual basis. So the perspectives that we gain here only highlight the magnitude and complexities associated with large-scale global carbon capture that are to address climate change, but we will be faced with large decisions that have many aspects to them going forward. So with that, I thank you for your attention, and I look forward to the live stream discussion. Thank you.